Okay. Now to go with this particular communication system, whatever we find, which will be made with different wherein this OFC cable or whatever the intermediate fiber connections or joints we are trying to establish for this channel. So that will be depending upon the link length. Right? Now I should know what is exactly the distance covered or to be covered. Right? Now based on that particular length, I will be establishing some repeaters over there. Okay. I can call these as repeaters, or sometimes I can call these as amplifiers. It means I'm going to strengthen the signal over here. Correct. Next, see, we do not always try to establish a communication link using OFC cables only in terms of meters or centimeters. Okay, it will be usually in terms of kilometers. Correct. Now, so you know all the what the BSNL, which is trying to establish the landline connection now. Now it is trying to use these OFC cables. It means it is going to cover a lot of distance in terms of kilometers, maybe it in terms of 200 kilometers or 500 kilometers somewhere. Correct. Now, even these different types of OFC cables, even these are used underwater. I mean, in what submarine systems and all. Okay, we have a lot of such examples which will be carrying the light signals through this OFC cable for hundreds of kilometers. Okay, and not only there is an increase in distance, but there is even the transmission rate or the bit rate is also high enough. Okay, it is in terms of gigabits per second. Okay, so for example, if we try to install it in a digital systems, okay, which will be trying to cover a range of 40 to 60 kilometers, there the bitrate will be somewhere in between 2.5 to 10 gigabits per second. It means for 1 second it will be trying to send 2.5 gigabits. Okay, now one example he has mentioned, that is Transatlantic optical fiber system. So here it is covered for a distance of 6,000 kilometers. Okay, and it has somewhere around 120 optical repeaters. Okay, I mean with a distance of 50 kilometer, they have placed each repeater, and here it is capable of carrying 32 wavelength division multiplexed channels, and here the bit rate is 10 gigabits per second. It means, see, the distance covered is 6,000 kilometer, and the repeaters used are 120 at a distance of 50 kilometers each, and what per second 10 gigabits are being transferred, and we have 32 wavelength channels. I hope you already know what do you mean by WDMA or WDM. Okay, that is wavelength division multiplexed channels. Okay, it means it is trying to what divide the wavelength. Okay, with respect to the multimode, when we have a lot of light waves entering in, all those will be with different wavelengths. Okay, those will try to multiplex and divide it. Then we will be trying to what send those light waves at different instances. Okay, to reach the receiver part. And that is what usually we will be calling it as a WDM. Okay, now one more experimental what the setup here we have is, which will be covering somewhere around 4,800 kilometers, and it is carrying again 10 gigabits, and it has 64 WDM. See, it means here we are going to talk in a huge number. It means my OFC cable or OFC communication should be strong enough to make or to lay and what a good communication system with what with good transmission rate, with longer distance covering. Correct. It means these two are very, very important: distance and the transmission rate. These should be good enough. Okay, now here the transmission rate, usually it will be talked in terms of gigabits per second. Okay, and the what the distance it tries to cover will be in terms of thousands of kilometers. Okay, then only we can call this as what an optical fiber as a telecommunication link. Okay, next. Now, when we try to what talk with respect to communication system using fibers, okay, we may go with fiber to fiber communication. Of course, it should be always a fiber to fiber communication only. And sometimes I may connect some electronic devices to this fiber cable. It means fiber to device or fiber to electronic device or fiber to electrical device. It could be anything, any coupling may happen over here, fiber to fiber or fiber to any device. Correct? Or it may be fiber to air, then air back to fiber. Correct? It means different types of connecting systems will be available in this OFC communication system. Okay. Now when we try to do this, okay, it should increase the number of what the terminal communications or connections, so that I can be able to withdraw the light waves which are passing through this with n number of ports. Okay, even that should also be possible to what, to receive the light wave in different channels. Or if I want to divide it, see for example, I have one input, I try to give it for 4 outputs. Correct? It means I am going to connect 4 optical devices or 4 fibers for a single input channel. Okay, even such things should also be supported using this OFC telecommunication link. Okay, now with respect to this, a lot of development has been made. Okay, now we have 2 major categories to study this fiber joint now, which is still in development. Okay, now what those are? Now the first one is fiber splices. Okay, see, these are semi-permanent or usually we will be calling this as permanent joints. See, we will be sometimes using T joints, correct, with respect to pipeline system. It means we are not at all going to remove those joints. Such joints usually we call as permanent joints or semi-permanent joints. Okay, now here also in OFC we will be using such semi-permanent or permanent joints. So which will be used in this OFC telecommunication systems. This is something similar to the electrical soldered or the joints which we are trying to use in electrical system or even the domestic, that is pipeline system. Okay, it means these are permanent. And one more is demountable fiber connectors or simple connectors. Okay, 2 things. One, fiber splices, which is semi-permanent or permanent, and one more is non-permanent. And that non-permanent will be calling as demountable fiber connectors or simple connectors. Okay. Now, these which are the simple connectors. Okay, these are removable joints, which are very much easy to what, connect or couple and uncouple the things. Okay. Now, to give an example for this, we have the electrical plugs or sockets where we will plug in and remove it out. Correct. See, the charger which we use for laptop or mobile, which is what, a pluggable. Correct. Now, such things or such connectors we will be calling as demountable or removable joints. Okay. Now, even this is also used with respect to what, the OFC cables. Okay. Next, see the fiber to fiber joints which are designed. Okay, these will be coupling all the the light which is propagating from one fiber to the adjoining fiber. Okay, now if I make a light wave to travel from the input fiber, then I will be coupling another fiber over here. Then I have to make this light wave to pass through the next fiber which is connected through some joints. Okay, and even we can use, as I just mentioned, even we can use some branching devices. Okay, now what these branching devices will do, I want to split this light wave into some devices which I have connected to branch it. Even it may be 2 or more fibers, or even I can use some devices also, as I just mentioned. Okay, now one more thing even we can mention over here is I can make this as bidirectional. Okay, see exactly T. See, with respect to T, how is it for the T which is a vertical line, I will be giving input and I can extract the 2 outputs from a single input channel. Okay, now this is also possible with this OFC link or OFC cable. Okay, now we'll study the alignment and the losses where the fiber is joined. Okay, now, so with respect to what the different types of fiber to fiber connection which we try to establish at the interface. Okay, even though the jointed fibers, whatever we find, even though it is smooth and even though it is perpendicular to the fiber axis, see, observe the thing here, even though the ends are smooth, means not blunt or not cut in a different what manner so that light wave may lose. No, it is with smooth ends, and it is what with respect to perpendicular to the fiber axis, means the axis with respect to first cable and the axis with respect to second cable should be in line, even though if it is okay, there may be, I mean, the two fiber axes are perfectly aligned. Okay, there will be some amount of light wave reflecting back into the transmitting fiber. Okay, what do I mean by the axis of first cable and the axis of second cable? When light tries to enter in the axis of the second cable, correct, the light wave, some amount, some proportion of the light wave tries to reflect back practically. Okay, theoretically we may speak as there may be no such losses, or there may be no such reflection loss, but still practically some amount of light wave will reflect back into the transmitting fiber or the first fiber. Correct? So this phenomena we will be calling as Fresnel reflection. Okay, I hope you have heard the Fresnel, Fraunhofer, all those. Correct? Now this Fresnel reflection is nothing but what? Small amount of light which gets reflected back into the transmitting fiber, which causes some attenuation loss at the joint. It means now due to this joint, some amount of light will be sent back or reflected back at this interface or at this joint. Okay, such attenuation we will be calling as Fresnel reflection. Okay, see now what is the interface here? Glass, some small part of or small amount of air, then again fiber. It means glass, air, glass. So this is what the interface we find over here. Correct? Now whatever the amount of reflection happens here, okay, I mean whatever the attenuation or whatever the what the magnitude of this reflection happens over here, okay, we can try to estimate it. Okay, and that estimation is done using one classical Fresnel formula, for that is for light of normal incidence. Right, it means we will make a light just to enter normally in the what second fiber axis, but still due to the reflection, to calculate this reflection amount we have a small equation over here. Now what is that equation? R is equal to n1 minus n divided by n1 plus n whole square. Now we already know what is n1. N1 is what? It is the Ri of core. And what is n? Now here we usually ignore the cladding part here. Okay. Ignore means we don't need that cladding part here. It means now we are only concentrating on the core material. Okay. It means I'm trying to establish core to core. Okay, but that thing is not possible. It means some amount of air do exist during such joints. Okay, that is why we get an interface like what? Fiber or the glass material, then air, then again glass. So this equation is what? R is equal to n1 minus n divided by n1 plus n whole square. Now what is this R? This is a fraction of light which is reflected, and we know what n1 will be with different value, or usually it will be 1.5, and the n which is the refractive index of air, usually it will be 1. Okay, now based on this R I can calculate even its loss. I mean we will be calling this as Fresnel loss, and this loss we will be trying to express in decibels. Correct? And that loss due to Fresnel reflection is given by minus 10 into log of 1 minus R to the base 10. Okay, now these two are the equations which are used to calculate the what? The partial reflection and the loss due to this Fresnel reflection. Okay, these two are very important equations. Fine. Now can we try to reduce this loss? Yes. Now whatever the Fresnel reflection we are trying to get over here, okay, we may reduce this Fresnel reflection. Now how? It means whatever the effect of Fresnel reflection we do find at fiber to fiber connection. Okay, now how I can reduce this? It can be reduced by using one fluid, that is index matching fluid. Exactly that will be applied between the jointed fibers. It means where exactly we find a fiber joint. At that point, we are going to apply this index matching fluid. Now, what is this index matching fluid? See, here we have three indices, N1, N, and N1 again. Of course, N1 and N1 should be same, correct? But still, I have one different Ri in between. Correct? The fluid which we are trying to apply at this joint, it should be index matching. Now, on usage of this index matching fluid at the joint, okay, we may try to reduce, or we may theoretically we may try to remove this Fresnel reflection or the loss due to this Fresnel reflection. Okay. Now, see, this is one of the what a good source of optical loss at fiber joint. Okay. Next. Now, whatever the fiber to fiber communication which may happen over here, okay, again it may be due to misalignment of those different fibers. Okay, and those misalignments we will be studying in detail in the next part. Okay, now we'll do one simple problem on this. What that problem is? Simple problem, again direct substitution, that's all. See, this OFC cable has Ri of 1.5, that is core Ri. Then two lengths, see these are again what smooth and perpendicular as mentioned, and these are perfectly aligned. We need to calculate the loss in decibels. Okay, now first we'll calculate R is equal to what? N1 minus N by N1 plus N whole square. So N is 1 point, sorry, N1 is 1.5 and N will be 1. Why? This is the Ri of air. Okay, so it will be 0.5 divided by 2.5 whole square. I'm going to get it as 0.04. Okay, it means there is a 4% of what the transmitted light getting back. Clear? If I have 100% of light emitting, 4% of that particular light wave enters back into the transmitting fiber. And this is what this 0.04 means. Next, we try to calculate the Fresnel loss or the loss due to this Fresnel reflection in terms of decibels. Now, in terms of percentage, 4. In terms of decibels, we need to calculate it. Now, how is it? Minus 10 into log of 1 minus R to the base 10. Okay, so minus 10 into log of 1 minus 0.04 will be 0.96 to the base 10. If we just calculate, I'm going to get it as 0.18 decibels. This is a simple the direct substitution problem, wherein just remember the simple equation, that's all. N1 minus N divided by N1 plus N whole square. Okay, wherein I will be getting the magnitude of the reflection. Next, now we'll study the three possible types of misalignments which may occur now during the joints. Okay, the first one. Now, what does that A stands for? The first one is longitudinal misalignment. Okay, now longitudinally, when I try to connect, there may be some change in the diameter of both the cables. Okay, that is longitudinally when trying to align. Next, lateral misalignment. See, the B exactly it indicates. See, there is some missing of the fiber cable during coupling or during the joint. Next is the angular misalignment. Okay, see, if I try to hold the pipe exactly matching both the surfaces or both the faces exactly, then there may be a chance of making a light wave to pass through. But if I have some certain angle, okay, I just tilt and I just hold both the pipes. It means there will be again the misalignment over, and there will be some with change in angle. Okay, see the axis with respect to fiber 1 and fiber 2, it should be continuous. Correct. Now, if I have a certain angle over here, I am going to get the misalignment over it. Means these are the three possible cases of misalignments with respect to the OFC joints. Okay. Now, okay. The next one. Now we'll try to study some figures or the numbers associated with these three different types. Okay. Now, there may be some What some deviations in geometrical properties or some optical parameters of both the cables, which are trying to uh, what during the joints or during the optical communication, the parameters which we are trying to what use for both the cables, there may be some deviations. It means both the parameters may not match sometimes. Okay, for example, the fiber 1 and fiber 2 may have fabricated at different what specifications. Of course we should try to maintain the same specifications, but practically sometimes what happens, there may be some deviations in this geometrical as well as some optical parameters. Okay, now due to which we will be getting insertion loss, or I'll be calling this as optical attenuation loss. Correct. Now whatever the inherent problems which we are trying to get while joining, okay, those again those may be due to now what just I specified as optical parameters or geometrical parameters. Correct. Now those optical parameters may be core and cladding diameters. It means the diameters may not match the first parameter. Okay, what is that? The first parameter is the diameter. The core and cladding diameter may not match sometimes. Then the numerical apertures are or the delta may not match. And next, the refractive index profiles may not match. For example, what if I have a parabolic in first transmitting, and in the second fiber I may have what a triangular. It means here the profiles may not match. Okay? And there may be some fiber faults. Okay, now due to all these, okay, we are going to get attenuation losses. Correct? And such losses we usually call these as intrinsic joint losses. What do usually called as intrinsic joint losses. Okay, these are completely due to Fresnel reflection, and this Fresnel reflection will be due to what? Those misalignment kind of thing. Okay, next. Now whenever we try to manufacture the fibers, we should be aware that these are compatible fibers, or the same fibers are used for similar application, so that its tolerance should also be less, or lowest tolerance should be there. Okay, now okay, whatever the three different types of losses or misalignments we have seen, those will be longitudinal. And if we talk of the what lateral misalignment, those may be with respect to what the fiber core axis, and the last one will be the angular measurement. Okay, the next we have some what the numerical values given over here in terms of decibels. Okay, some what uh, when there is a change in the what diameter, that is 50 micrometers, then numerical aperture when it tries to change. Okay, all those change in those optical parameters may give you different types of what the losses. Okay, again we have similar kind of what the analysis of all those numbers or numerical values in terms of, sorry, not working. Okay, yeah. Yeah, we have done this problem. Yeah, we are with this. Yeah, I have some graph over here. Now, what does this graph mean? Okay, we'll see that graph quickly. Now, what is that graph? See here. Now, with respect to displacement and with respect to the losses. Now, how exactly we can analyze this? As there is a displacement in terms of longitude, or in terms of axial or radial or lateral, or in terms of angular. Okay, as there is a displacement or there is a change, we are going to get a lot of insertion losses. It means laterally it is going to increase. Okay, and after some point the lateral whatever we find here, it stops means it will be somewhere constant for some certain value. It means beyond the displacement value it may not exceed. But if I consider the longitudinal misalignment, correct? See, this is how it goes, the line. Okay, the insertion loss will be not much in longitudinal. Correct? Why the insertion loss is not much in longitudinal? Okay, the angle will be same. Correct? It means there is no change in the angle. Correct? It means I am trying to, or we are trying to hold both the fiber cables along the axial length. It means only at the joints there will be some proportion of light waves getting back longitudinally. Laterally, if we consider, yeah, there is a misalignment, so it tries to increase. Okay, till some what distance it tries to increase, and later it remains almost constant. Okay, these are the two different types of what the analysis of losses with respect to displacement. Okay, and with respect to angles, see here. Now, whatever the angular misalignment we studied, okay, now that angular misalignment will be completely depending upon the numerical aperture. See here, we have shown completely depending upon the numerical aperture means I have one certain value here, that is 0.22. Okay, now for that numerical aperture, which is an acceptance cone, okay, we have three things over here: index matched, air gaps, or two things rather than we can. Okay, air gap, why I mentioned two times here is the top part and the bottom part. Okay, for that. Now, see the loss with respect to core, see it is more. As I already mentioned, with respect to cladding part, usually we try to ignore it. Not exactly ignoring, we just put it secondary. Only with respect to core, wherein we are trying to match the gap, that is index matching, core to core, in between air. Okay, that air gap we are trying to ignore it. Correct? And during that particular what the joint, we are trying to apply that fluid. Just try to reduce the what the reflection loss. And that graph is something like this. See, again, as that angle increases, the loss will increase. It means, see, just try to hold the pipe by changing the angle. Okay, now hold the both the pipes in your hand and deviate or try to move away those both the fibers. It means as you increase the angle, or the entire ray or the light wave may try to come out, and even there may be no chance of even a single light wave entering in the second cable. Correct? Now that thing is analyzed using this what the misalignment with respect to the angle. Okay, now next we'll move with the multimode fiber joints. What exactly is this multimode fiber joints? Yes, we'll see this. See, theoretically or experimentally, whatever we are trying to study here, okay, here we are going to encounter certain losses due to misalignments and all. Again, those losses will be calculated, which will be again due to those three things: lateral, angular, or longitudinal. Okay. Now, there are a few what scientists or the researchers who have calculated theoretically. Correct? Now, what they have calculated is, as we just discussed, the losses due to the longitudinal misalignment, it is treated almost as a zero. Correct? See, see, the two group of workers, they have what done a research, and they have clearly agreed that, or based on experimental results, the longitudinal losses are very much, or they are not at all going to agree that there we don't have any losses in longitudinal misalignment. Because experimentally they have proved it. Because they are going to disagree that there is a loss. Okay, we just to confirm here that for a longitudinal misalignment, usually there is very minute amount of loss. That's all. Okay, next. Now, with respect to this lateral and angular misalignment, okay, we have a definite loss over there. Okay, and that again experimentally they have proven it. And those two persons are what something like Miyazaki and Tsuchiya. Okay, these are the two teams of workers. Just they have worked on this experiment and they have come up with some solutions. Okay, Next, now what we will try to reduce the the lateral misalignment. Now how we can try to reduce the lateral misalignment? So this lateral misalignment can be reduced by reducing the overlap region. What is that overlap region? If I try to hold both the OFC cables exactly touching both the tangential surface, it means it should not overlap. Okay, if I try to reduce this overlap region, then the lateral misalignment may be reduced. Okay, now here we need to assume that there is uniform excitation throughout this or the optical mode in this multi-mode step index. Okay, and this whatever the coupling we try to do here, it means by reducing the overlapping region. Okay, now we try to calculate its efficiency or the coupling efficiency. Okay, see here again we are trying to use a multi-mode over here. Okay, then only we can easily analyze the misalignment kind of things over here. Okay, now what is that? The coupling efficiency, if we try to calculate it, that is given by eta. Okay, we know this symbol eta laterally. Okay, and this we will be calling this as a lateral coupling efficiency, which is given by eta lat. Okay, and this is for two similar step index fibers. Okay, even though if we consider both the step index fibers as the same, but still we are going to get some amount of losses due to lateral misalignment. Done. And what that equation is? Very simple equation, but lengthier, which will be involved with refractive index of core, cladding, then diameter. And what is that y? That is the offset. That is y is the lateral offset of axis, both the axes. Okay, and a is the radius. Okay, that is eta lat is 16 n1 by n whole square. I hope you can see the equation. Okay, a little lengthier equation, but we can remember it easily. Here, n1 is what? Ri of core, Ri of air is n, y is lateral offset, and a is the fiber core radius. Now, if I want to calculate this in terms of decibels, so again simple, minus 10 into log of that eta lat to the base 10. Okay, so using this equation, we can easily calculate what this efficiency. Okay, next we'll see the same thing if I want to express or what for what the considering small lateral offset, that is whatever the lateral misalignment loss, if we consider it for graded index fibers. Okay, now the earlier equations holds good for step index fibers. Okay, now the same concept if I want to apply for graded index fiber. Okay, wherein the distribution of optical fiber throughout all those guided modes will be uniform. Okay, now if we try to estimate that lateral misalignment loss, which again depends on the Ri, the refractive index gradient, that is alpha. Now that will be obtained from this equation, that is LT. We'll be calling this as LT. And what is this LT? See, LT is nothing but what? It is the lateral misalignment loss with respect to graded index fiber, considering Ri of that small lateral offset. Okay. Now what is that equation? That is simple equation. See, we have a lot of equations over here. We need to remember all those. Okay. And what is that LD? I guess see, again this is loss only. Now what the long equation we had with respect to step index, similar equation we will be having for the gradient index. Correct? And here alpha will be what? This is a small lateral offset. That's all. Or we will be calling this as refractive index gradient alpha. 2 by pi y by a alpha plus 2 divided by alpha plus 1. Okay, and we have one condition here. The the y value, it should be in between 0 and 0.2 times the radius. Okay, And the efficiency for this, I mean lateral coupling efficiency for this graded index fiber will be 1 minus LT. Okay, next. Now in terms of decibels, we just divide it, 8 divided by 3 pi. Okay, now we know usually these OFC cables will be with parabolic refractive index. So its value, alpha value will be 2. Just substitute that alpha as 2. Okay, you will be getting certain value over here. Now you may ask me how you got this. Correct. Now utilizing what the refractive index profile, I mean parabolic refractive index profile, where alpha is equal to 2, just substitute that value. 2 plus 2 divided by 2 plus 1. Okay, if we just simplify it, I will be getting 1 minus or LT as this value. Okay. Now ultimately put this LT to calculate its efficiency. 1 minus what you will be getting on knowing the things Y and A. Okay. Next. Now we have one problem on this. Again, direct substitution. We have Ri as 1.5 and diameter is 50 micrometer, and the core axes are of 5 micrometers each. Okay. Here we need to find out what uh, insertion loss. Okay, at the joints, which will be due to misalignment. I mean, particularly lateral misalignment. Okay, that coupling efficiency calculated first, then I will be getting what the loss, lateral loss. Okay, use that long equation. Now here somewhere now we need to use either equations depending upon what type of fiber. Okay, see this is a step index fiber. Step index fiber means I have to use this long equation. Okay, please be careful while using the equations. Okay, we have different coupling efficiency and different loss equation for both step index as well as graded index. Okay, for step index, this is the equation. Clear? Now, yeah, N1 is 1.5, N is 1, it will be 1 for air. And what is this Y? Y is given, which is 5 micrometers. Then A, what is A? At the diameter is 50 micro, A will be 25 micrometers. Okay, now just substitute and simplify. You will be getting 0.8. Now try to calculate this in terms of decibels for the insertion loss, which is due to this lateral misalignment. Okay, now minus 10 into log of that 0.804, you will be having 0.95 decibels. Okay, next. Assuming a small air gap at the joint, the insertion loss is approximately 1 dB, and that lateral offset will be 10% of the diameter. Okay, next B. It means based on the above calculation, we have this statement. Okay, 1 dB decibels, 1 dB loss. Next, what is B? What we tried to calculate? The joint is considered as index matched. Okay, earlier it was small air gap. For that air gap, we considered N as 1. Now the joint is index matched. Now, if it is indexed matched, yeah. If it is indexed matched, now this is the equation. It means no air gap. It means both the fiber cables are longitudinally correct, axially correct, radially correct. It means we don't have any air gap over there. Yeah. Now for that, we have an equation. So it is 1 by pi entire. 1 over pi, 2 into cos inverse of, yeah, y by 2a minus y by a into 1 minus y by what 2a square whole under root. Okay, just try to remember these equations. Okay, now based on that efficiency, I can easily calculate the insertion loss. Okay, and that value again we are trying to use it over here. Y value is 5, A is 25. So LD I'll be getting something like 0.128. Now lateral coupling efficiency will be 1 minus the LT. So 0.872. Now calculate its loss. It will be 0.59 decibels. Okay. Now this is a simple problem on it. Now we'll calculate for a graded index fiber. Okay. Now for a graded index fiber, the equation is very simple. Correct? It is just what? The equation will be 0.85 into y by a. Very simple equation. 0.85 into y by a. Okay. Now what are all the given things here? This is parabolic. So alpha is 2. Core diameter is 50 micrometers. And we need to calculate what? Insertion loss. And we have y as 3 micrometers. Okay. Now we need to calculate this for two things again. One for guided modes only, and second for guided as well as leaky modes. And that leaky modes is nothing but what? Due to lateral misalignment and due to angular misalignment. Okay. Now those two things we need to consider over here. Now the first LT 0.85 into y by a. Y is given, which is 3 micrometers, divided by a, which is 25 micrometers. Just calculate that LT, simple. Now eta lad means 1 minus that 0.102 or 102. So 0.898, and use it with respect to log. You will be getting it in terms of decibels. Next. Now with respect to what? Leaky modes. Now with respect to leaky modes, LT will change. What is it? What is it? 0.75. Instead of 0.85, it is 0.75. You can see these are what, based on some experiments, they have what? Given these equations. Okay, there is no derivation for this. Okay, these equations are derived completely based on experimental results. Okay, 0.75 into y by a. Simple substitute. Okay, calculate all those in terms of what? The efficiency, then in terms of decibels. Okay, now it means the losses which we are trying to analyze, okay, will be different for step index and will be different for graded index based on the equations which will be employed over here. Done. Now we have one more insertion loss, which is due to lateral misalignment for multi-mode graded index fiber. That was considering angular misalignment. Okay. Now for angular misalignment, we are trying to calculate its angular coupling efficiency. We will be calling this as angular coupling efficiency, which is given by eta angular, that is eta anc. Okay, again it has got its own equation. 16 n1 by n whole square divided by 1 plus n1 by n whole raised to 4. Okay, see again this is a direct equation. And this equation will be referring for angular misalignment losses for multi-mode step index fiber. Okay, just try to remember this. Again, I repeat, this is an equation for angular misalignment loss at joints for step index. Okay. Now, similarly, if I want to calculate it in dB, again, say minus 10 into log of that eta. Okay. Now, again, what we try to use this formula to calculate few things over here. We will be calculating angular coupling efficiency. Okay, again just direct substitutions, that's all. N1 will be how much? 1.48. N is N is 1. Then NAs are given. Okay, and now what will we have delta component here. Okay, now based on that delta I can calculate NA. Now NA are given, numerical apertures are given. Okay, now for two different values, okay, we'll see this problem quickly. Now what the problem here is, now I need delta. Okay, and that delta can be calculated using numerical aperture. Correct? Okay, we'll see. Now what are all the given things? Step index fiber with numerical aperture of 0.2 and 0.4. Ri, that is N1 is 1.48. I have to calculate insertion loss at 5 degrees. Okay, this is what the thing given in the problem statement. Next. Now what I'm trying to do here is, now where I have delta here, that delta I'm trying to put it in terms of Na. Now we already derived this, okay, in the first module. Na is approximately equal to N1 into 2 times delta. I mean under root of 2 times delta. Correct? Now that I am trying to use it here, that's all. N1 2 delta, which is under root, is nothing but what? Na. Directly I have substituted. And this, using this different value of Na, that is 0.2 and 0.4, will calculate. First we'll calculate it for 0.2. Okay. Eta angular. For 0.2 it is 0.797. Okay, again based on some simple substitutions, that's all. See theta, I will be making it with pi by 180. You know why? Okay, simple. Now calculate its loss and go for next Na, that is 0.4. Similarly, you will be getting eta angular as 0.862 and use it for calculating it in terms of decibels losses. Okay. Now here we have what? Here we need to assume what the multimode step or the multimode gradient index fiber are equally exciting with respect to same index profiles and same numerical apertures. We have two set of equations over here. It means the loss which is resulting from mismatch of four diameters. See here we have two different diameters, A1 and A2. A1, A2. Okay, this A1 and A2 are nothing but what? A1 is a radius of transmitting fiber and A2 is what? It's a radius of the receiving fiber. Okay, now based on those two radii or radius conditions, we have a certain equation here or loss here. What is that? If A2 or the radius of transmitting fiber is more than the radius of what? Receiving fiber, then the above equation, I mean the first equation, minus 10 into log of A2 by A1 whole square. If the diameter of receiving fiber is more than or equal to the the radius or diameter of what transmitting, then the loss will be 0. How? So you can think. Okay, almost the loss with respect to the CD will be 0. Okay, this is what with respect to what the losses. Now, if we have studied two different types of losses here. Insertion loss, considering different phenomena over here. Okay. Now, okay. If you have any doubts till now, you can ask. See, this is completely based on some experimental results, formulas, and very simple concept. That's all. Okay. Only thing to remember here is some formulas and why these joints are required or what these joints will do and how exactly the coupling should be done and what will be or why there will be what the losses which will be due to three misalignments. Okay, that's all. Okay, this is what with respect to different types of what the joints or the losses due to joints or at the joints. Okay. Let's stop here. In the next class, we'll move with the further points which will be studied with respect to single mode. Okay. And today we have done with multi-mode and all. We'll be doing it with single mode, then splicing and all we will study. Okay, in the next class. Thank you.
Thank you, sir.